Okay, so we'll hope more number of people will join because that was a serious mistake actually. Yeah. So, anyways, the recordings of the meeting can still be accessed by those who are interested because it will be shared once the meeting is over. So it'll be updated in YouTube, and like if anyone wants to review what has been discussed in the meeting, they can always go back to the meeting. Okay, so yeah, maybe we'll start with the session. Could you introduce yourself, Saurav? Have you been through the entire week one lectures?
Yes, sir. So I'm
Yeah.
Saurav, and I'm currently pursuing my final year aerospace engineering
Oh, okay.
from Bangalore.
Yes.
And yes, sir, I have been through the first week's lectures, and
Okay.
I haven't solved the assignment yet.
Okay.
So
Yeah. So how do you find the
yes, sir.
lectures? I guess
The
the deadline is,
lectures,
it's on 9th or something, I suppose. It's not.
yes, sir. It's on 9th August, sir. So I found the lectures fine because actually I have done several courses on flight mechanics before.
Okay.
So
Yeah.
a lot of the stuff on rotations and transformations are I'm familiar with that. So
Okay.
it's not a problem for me. So
Okay. So
but I'm comfortable with it. Yes.
okay, so more or less you will be using the same notations, I suppose, in regarding to the transformation between different frames and all those things. So yeah, it will be
Actually,
more.
so I would like to mention one thing that
Yeah.
in aerospace we have a little bit of a difference in the like I found a small difference in the
Okay.
rotation and the DCMs, the direction cosine matrices.
Okay. Yes.
So
Understood. I
like
guess it'll be the
yes,
transpose, I suppose, right? It'll be the
not
transpose of.
exactly the transpose, sir. What I have observed was that over here in this course we have the RZ alpha. That was
Yes.
like cos alpha minus sine alpha cos alpha.
Okay.
But on the other, for RY beta, that was cos beta sine beta. So
Yes.
in aerospace, it was what I had observed was cos beta and then minus sine beta on the top, like cos beta 0 minus sine beta, then 0 1 0, and then
Okay.
sine beta 0 cos beta. So
Okay. That is only regarding the particular rotation about y-axis, I suppose.
yes,
Rotation metrics that we
yes, yes, that's right.
have.
Yes.
Yeah, well, I suppose that is still the same in our case also, right? Like if the rotation is purely about y-axis, then we'll get the same rotation metrics, like whatever you said, cos
Mm.
beta 0 sine beta, then 0 1 0, then minus sine beta 0 cos beta. We
Yeah, but actually we get cos beta 0 and then minus sine beta on the top, like
okay.
in the course which I did in my
Hmm.
college.
Okay.
So yeah,
I
but
guess
I think I'll
it's still the transpose, right? It's the transpose of whatever
yes,
we have discussed, I guess.
yes, that is right.
Yeah.
So
Hmm.
I still need to go and review those a bit, but
Okay.
besides that, I'm comfortable with everything. So no
All right.
issues with that.
Okay, no problem. So we also have one more participant. I guess, yeah, with the information that we have shared, I guess it could be a bit difficult for the students to join because the information that we have shared is not, it doesn't seem to be correct actually. It turns out it was something else. So anyway, like we have, for the time being, we have shared it in the discussion forum. So I hope more number of people would see it. Okay, so we'll get on with the session. Yeah, I am myself Isaac John. I am a PhD scholar from IIT Palakkad. I work under the direct supervision of Dr. Shantakumar Mohan, who is basically taking care of this course in NPTEL. So on the previous sem, he actually he offered a course on wheeled mobile robots, and for this sem, for the sem that starts on July, uh, he's basically offering the course on manipulators actually. So earlier it was wheel mobile robots, and for this semester it is manipulators. So yeah, if at all, if you are facing any issues in the sessions, whether it is my audio visuals or if you are not following something that I'm saying, or if anything like anything at all you are finding difficult to follow, please let me know. Okay, so yeah, this being the first session, I have prepared the session on my own style. So maybe if you have any further suggestions that I can take up in the later sessions, please let me know. So we'll basically cover with a small summary of the topics that we have discussed in week 1, and later we'll go through some sample problems, on the lines of the assignments that you could that you would be required to solve. It'll be more or less on the slide on the same lines. So yeah, coming on to the syllabus of week 1, we basically covered an introduction. A section was on introduction to robotics. We basically covered a definition of robots based on different organizations or different societies. And later on, we also encountered a section on introduction to robot mechanics that is specific to robot manipulators, more or less in the framework of our course. Then on the later sessions, we also introduced one of the most fundamental problems of robotic manipulators, which is forward and inverse kinematics. Then later on, we'll discuss on how to represent the position and orientation of rigid bodies. We'll also introduce the concept of transformation matrices, and also some key points regarding compound rotations, like rotations involving multiple axes. Okay, so going on, the first section basically deals with the definition of few of the key terms that as a roboticist we should be more or less aware of, especially as someone who is taking the course for the first time. So it starts with the definition of robot as provided by the Robot Association of America. It basically says that an industrial robot is a reprogrammable, a multifunctional manipulator designed to move materials, parts, and tools, or specialized devices through a variable programmed motions for the performance of variety of tasks. That is a standard definition that is given by Robot Society of America. And a more modern definition that is in line with the time that we are living with basically says something more or less derived from the classical definition. It says an intelligent agent. Sorry, a robot is an intelligent agent, be it physical or virtual, capable of doing a task autonomously with or without guidance. For example, chatbots. So this more or less covers a broader domain that what the classical definition dealt with. And yeah, so like it can have a lot of definitions, like a lot of societies or a lot of fields that robots are associated with comes up with their own definitions. And yeah, if we are sticking strictly with the framework of the course, the most ideal definition as per the framework of the course is this: a robot is an electromechanical machine or a mechatronic system with sensors, electronics, and guided by computers controllers. So it basically says a robot is basically a collection of linkages, or it's basically a machine which is actuated using actuators. It can get its feedback from the sensors, and it will use all the electronics and the controllers used to automate whatever the robot is supposed to be doing, which basically gives its control, which basically gives the brain for the robot to perform its tasks. And regarding on where and when to employ robots, this is where we would use the robots. It's called the 4D of robots. 4Ds are basically the tasks where if you are employing a human being, they would find the tasks to be dull, dirty, dangerous, and difficult. And it is on these sort of tasks that where we are employing robots as opposed to humans. Moving on, the first section also introduces a term called effector. So what it says is, if an effector is any robot or a robotic device that has an effect on the environment. So I've given 3 different examples of effector. So over here is an example of an effector. Over here is an example of an effector. Over here is an effector of an example, an effector. So yeah. So what are the different kinds of effectors? So over to your left hand side, this is an effector, but the purpose of this effector is used to manipulate the objects around it, right? To manipulate the objects around it. So there is a broader term for these sort of effectors. These are called manipulators, where their sole task is to manipulate the objects around it. And on the second figure, this is also a different kind of effector, but they comes under the classification of mobile robots, where in the case of mobile robots, the effect on the environment is the motion of the effector itself, right? But in this case, the effect on the environment is the motion of the objects around it. And in case of a mobile robot, the effect on the environment is the motion of the effector itself. And on the third case is basically a combination of manipulators and mobile robot. We call these systems as vehicle manipulators. So this would have the combined features of both the manipulators as well as mobile robots. And another term that we would introduce in this course is something called controllers. It is used to get the effectors to produce the desired effect on the environment, like be it manipulation of the objects, be it the motion of the effector itself, or something else based on the robot's tasks. So if the robot's task is to manipulate the objects, the controller would get the effector to manipulate the tasks. Or if the effector's task is to move itself or to locomote itself along within the environment, then the controller would get the actuators of the locomotion device to navigate within its environment. And same goes for vehicle manipulators. Yeah, and since the course is strictly on manipulators, I would also like to introduce you to different kinds of manipulators. But be aware that this is not an exhaustive set of manipulators. We still have even broader sets of manipulators that comes under the realm of soft robots. But for the time being, we'll limit ourselves within rigid manipulators, under which we have the following classification. So over to your left is a serial manipulator. And at the middle, you have something called a parallel manipulator. And at the rightmost end, you have something called a hybrid manipulator, which is basically a combination of a serial as well as a parallel manipulator. So in case of a serial manipulator, it consists of links attached from one to the other on the basis of head to toe. Like links are basically successively attached using joints. So each of these links, so this is one link, this is another link, and you will also have another link. So each of these links are actuated by their own actuator. So in order for you to actuate this link, you will have a motor over here. In order for you to actuate this link, you will have a motor over here. And for this link, you will have a motor over here. So yeah, motors are mounted on each of these links. And that is also its primary disadvantage, because in case of a serial manipulator, the most of the weight of the entire manipulator is contributed by the motors themselves rather than the links. So as you might have expected, if you have motors hanging over here, you may also have heavy motors hanging over here and here. It introduces a lot of rotational inertias. So that would basically create a lot of the accuracy of such robots where the motors are basically hanging on the robot. The accuracy is basically compromised. The positional accuracy would be more or less compromised because of the rotational inertias within the robot. Whereas in the case of parallel robots, you have multiple links that connects a fixed base. So if you consider the ground as the fixed base, you also have a top platform. So there would be multiple serial chains that connects the ground to the moving platform. And the applications where we would employ serial manipulators and parallel manipulators are entirely different. So in applications where we would require a large workspace and a high dexterous motion. Dexterity means like we can reach a particular position with multiple orientations. Or if you want a larger workspace, we would mostly employ a serial robot. But if you want But in case of parallel manipulators, we would employ it in applications where we would require heavy duty, high payload applications, high speed applications, and highly accurate manipulations. There we would employ parallel manipulators, right? And yeah, another feature of parallel manipulators is that not all the joints are actuated. In case of serial robots, all the links are actuated, but here only a select few joints are actuated. So in this case, the actuators are here actually. These are basically telescopic arms where you could manipulate the length of each of these arms. And typically, in case of most of the parallel robots, the actuators are mounted close to the base, or it could be mostly attached to the base. So it'll always remain fixed to the base. There won't be any inertia contributed by the actuators. So in that regard, the positional accuracy of parallel robots are much higher than serial robots. And if you are talking about applications, they are mostly employed in flight simulators where they would be used to mimic the motions of a flight, to mimic the motions of the G forces that a flight would encounter during its flight. And yeah, maybe in vehicle simulators also, in case of race car drivers, they would use these sort of platforms to simulate the motions or the forces that is exerted by a race car. And in case of hybrid manipulators, they combine the advantages of both serial and parallel robots. The serial robot would basically position the parallel robot, and the parallel robot is primarily doing the task. So task where a high amount of precision is necessary. For example, surgical robots. So in surgical robots, we would require a high amount of precision. So that is where we would use the parallel robot to make precise incisions. And to position the parallel robot's base, we would use a heavy duty serial manipulator. So it will have the advantages of both serial and parallel robotic manipulators. Yes. So coming on to a few of some definitions that is important during the course of the course. The first definition is manipulator. So manipulator is a system of a set of bodies or rigid links arranged or connected as chains with the help of joints. So as you might have seen in the previous pictures, it consists of a set of rigid bodies, and each of the rigid bodies are constrained using joints. So for example, like if we are considering a manipulator comprising of two links, we have one link over here, we have another link over here. So let this be the first link, let this be the second link. So the first link is connected to the base using a revolute joint, and the second link is connected to the first link using a revolute joint. And the revolute joint basically imposes 5 degrees of constraints. So like without the revolute joint, a rigid body can have 6 degrees of freedom. So in order for us to constrain a rigid body, we would use revolute joints, which would constrain 5 degrees of freedom, which are 2 rotations and 3 translations. And in case of prismatic joint, it would also constrain 5 degrees of freedom, which would be a single degrees of translation. And yeah, it would constrain 2 degrees of translation and 3 degrees of rotations. And there are higher order joints also. Like, for example, if you consider a spherical joint, it would only constrain 3 degrees of freedom translations, but it will allow the 3 degrees of freedom rotations in all 3 axes. So depending on the joints that you use, you would end up with different constraints, and these joints are basically used to constrain the links of a manipulator. Then another term that we would frequently encounter is something called a configuration. So that basically defines the complete specification of location of every points on the manipulator. So in this example, if this is a manipulator, the configuration basically specifies each and every point within the manipulator. So all the points within the manipulator would be fully definable. It should be fully definable. So in case if we are defining these angles, if I'm defining this angle as θ1, and if I'm defining this angle as θ2, if both of these angles are known, θ1 and θ2 are known, then we would be able to fully estimate the position of all the points within this manipulator. So that is basically what the configuration basically implies. And the third term we would be encountering is something called workspace of the robot. So as per the definition, it is basically the total volume swept out by the end effector as the manipulator executes all possible motions. So depending on the manipulator, the volume of the workspace could be different. The shape of the workspace could be different. The size of the workspace could be different. So there are robots that would give you a spherical work shapes. There are configurations or configurations of robot that would give you a cylindrical configuration of workspace, a cylindrical workspace. And within workspace, we have two subcategories called a reachable workspace and dexterous workspace. So I hope you can recall the definition of reachable and dexterous workspace, where reachable workspace are the points of the workspace where the robot can reach. But in case of dexterous workspace, the point can be reached with all possible orientations. So for example, if I'm attaching a robot gripper actually here, I hope you can see. And if this is a point, if this point can only be achieved by this configuration alone and no other configuration, then that point is called reachable workspace. At least this point is reachable. But in case of a dexterous workspace, so again, if I'm considering this as a point, and if the gripper can achieve this point in all possible configurations, it can achieve the configuration like it can approach this configuration like this, or like this, or like this, or any possible orientation. Doesn't matter. It can achieve this particular point in any orientation. So a collection of such points is called dexterous workspace. So I hope that is clear. Yes, and again, we also have a few more important key terms called a degree of freedom of a robot, that basically defines a minimum number of independent variables required to describe a system, or in other words, to fully describe a configuration of a robot. For example, like if we have a robotic manipulator comprising of two arms connected by revolute joints, this is first link, this is second link, this is the first joint, revolute joint, this is the second revolute joint. We would probably only require two variables, theta1 and theta2, to fully define the configuration of the robot. So in this example, the degrees of freedom would be 2. So depending on the physical architecture of the robot, the degrees of freedom could vary. But in a sense, it defines the minimum number of variables, the minimum number of independent variables actually required to fully define a system. And there is another term actually, degree of manipulability, that basically says the number of controllable inputs or number of active joints. So it's very easy to confuse these two terms, but in fact, it need not be the same. In this case, in this particular example, it is 2. The degree of degrees of freedom and degree of manipulability is still 2. Like the number of independent variables to define the system is 2, and the number of controllable inputs that we are giving are still 2, because we will be giving an input here at this joint and this joint as well. So in this case, the degree of freedom and degree of manipulability is still 2. But there are instances where we would give more number of controllable inputs. Like there are robots which have 7 active joints. So there could be instances where there could be some configurations in the workspace where the robot cannot achieve with 6 degrees of freedom. It's called singularity. You will come across later in this course. And in order to solve the singularity, some robots may have more than 6 active joints. So in that case, you could basically see a deviation between a degree of freedom and degree of manipulability. But in most of the cases that you would encounter within the course, the degrees of freedom would be more or less equal to the degree of manipulability. Okay. And again, there are a few more key terms that you might have encountered in the course regarding the kinematics. So kinematics is one of the most fundamental problems that one would have to solve in a robot, in the mathematical model of a robot. So basically, the kinematics describes the relation between the motion of the joints of the manipulator and the resulting motion of the rigid bodies which form the robot. So again, I'll explain that in the context of a 2-hour robot. This is the first link, and if we have a second link of a 2-hour robot constrained by 2 revolute joints. So this is link 1, and if this is link 2, yeah, the motion of the joints. So the motion of these 2 joints. So this is joint 1, this is joint 2, and this is link 1, this is link 2. And the motion of the joints are characterized by the joint variables labeled as theta 1 and theta 2. So theta 1 and theta 2 are basically the joint variables. And yeah, if we want the robot to do a task, mostly we would describe the task that the robot would be functioning or would be taking care of in terms of a different set of coordinates called task space variables. So mostly, if in the case of a 2-hour robot comprising of 2 links, we would mostly employ it in 4 positioning tasks. So the robot can at most manipulate objects in 2 dimensions, which are x and y coordinates. So this is what we call as task space variables. So x and y is what we call task space variables, and it is on the task space variables that we would define the tasks that the robot is supposed to carry out. And the motion of the robots would be motion of the robots would be defined in terms of joint variables actually. So typically the controlling of the robot would be happening on the joint variables. And yes, and the definition of the task would be defined on the task space variables. And the robot kinematics is what we use to map the task space variables to the joint space variables. So the mapping between the task space variables, both to and fro mapping between task space variables and the joint space variables, is taken care of by the kinematics of the robot. So as you might have observed, this is a 2-way mapping. So mapping from the task space variables to the joint space is called forward kinematics. And the other way, like from the task space to the joint space, is inverse kinematics. So I'll hang on 1 second. I guess the meeting is about to be over. The duration of the Zoom link was supposed to be 2 hours, but it seems that the license is only there for, I guess, for 45 minutes. I guess it's somewhat a problem from my side. So in case if the meeting is getting terminated, would you please try to rejoin the meeting within a few minutes? Would that be possible?
Yes, sir, it will be possible.
Yeah, this is the problem that we have with the first meeting. Like this Zoom link was supposed to have the license of the institute that is hosting, but it turns out that it does not have the licenses. It only has a regular license. So it may terminate within 8 to 10 minutes. So if that happens, you could try and rejoin. If that does not happen, maybe I'll anyway upload the videos, the full videos in YouTube. It'll be the links will be shared to you, and maybe you can catch up. If you have any questions, you can always raise the questions on the discussion forums. And hopefully by the next week, all the issues will be sorted out and we can have a smooth session. Okay, so yeah, continuing where we have left. Yeah, we were talking about kinematics, which is the mapping between the joint variables and the task space variables. Joint variable is where we would control the robot manipulator, and task space variable is where we would define the task which the robot is intended to carry out. So there are 2 problems actually, mapping between task space variables and joint space variables in different directions. So this is joint space, and this is task space. And the mapping from joint space to the task space, this is called a forward kinematics. Forward kinematics. So if you give theta1 and theta2, if we give the joint variables as inputs, then what is the position of the robot in xy coordinates? What would be the position of the robot's tip at x in terms of xy coordinates? This is the problem that the forward kinematics deals with. And the inverse mapping, like if we are instructing the robot to go to a particular xy, then what should be the joint variables? What should be theta1 and theta2? So this is the problem of inverse kinematics. Inverse kinematics. So I hope this will stay for us with for the duration of the course, because this is very important. So mapping from joint space to the task space is the forward kinematics, and the mapping from task space to the joint space, the inverse mapping, is called inverse kinematics. All right. Okay, so now we move on with the description of position of a point. So if the point P is denoted as such, then how would we describe the position of this point? Because a point does not, it is basically pointless to describe the orientation of a point, because it does not matter how the point is oriented. It's a meaningless quantity. So if we are dealing with points, we would be mostly interested to describe the position of the point. So it's straightforward. Like in 3 dimensions, we would require the x, y, z position coordinates of the point. It can be represented as a vector as such, with respect to a reference frame. So if the reference frame A be the global frame, let it be a global frame with respect to which we would be describing all the points of a robot. If you want to describe this particular point, it can be described with respect to a 3-dimensional vector. Each of the components would be the x, y, z coordinates of the point. Pretty straightforward, right? Yeah, and if you want to describe the orientation of a point, orientation of a frame, because now that we are dealing with orientations, we would be dealing with frames. So it's no longer a point. So how would we describe the orientation of a frame? So we would describe the orientation of a frame using something called a rotational matrix. It's a 3x3 matrix. And how do we populate the entries of the rotation matrix? That is how we are going to discuss now. So for the time being, consider we have a fixed frame. We have a fixed frame labeled as A. This is fixed with respect to the ground, or let this be the inertial reference frame. And we have a rotating frame, or frame B, that rotates with respect to the fixed frame of reference. Right. So the image that I have depicted over here is when the frame B rotates with respect to this XA axis. So initially, both of the frames would be coincident. Like XA would be coincident with XB, YB would be coincident with YA, and ZB would be coincident with ZA. And consider that we are rotating the frame B by an amount of angle theta with respect to XA. So if we are rotating this entire frame B by an angle theta with respect to XA, how would it look like? The final orientation of the frame B would look somewhat like this. Since we are rotating with respect to XA, XB would still remain coincident with XB. YB and YA would rotate by an amount of theta from their initial position. So this is theta. This angle would be 90 minus theta. And again, this would be theta, and this would be 90 minus theta. Now, how would we populate the rotation matrix? So we would populate it in terms of the columns. So we have 3 columns, as you can see. This is the first column, this is the second column, and this is the third column. And the first column corresponds to, yes, the first column corresponds to the angles that XB makes with respect to the original coordinate frame XA, YA, and ZA. So it's basically the dot product. So what is the dot product between XA and XB? The angle between XA and XB. That is basically, so essentially XA and XB are basically unit vectors. So their length are basically unity. So it's XA, XB, cos phi. In that case, cos phi, which would be the angle between XA and XB. In this instance, since both of them are coincident, the angle is basically 0. So cos phi would be basically 0. So what would be XA dot XB? The first term would be XA dot XB. That would be 1. And the second term of the first column would be XB. Sorry, I will rewrite it in this form. XB dot XA. This would be the first term of the first column. The second term of the first column would be XB dot YA. So that would be the angle that XB makes with respect to YA. So as you can see, both of them are orthogonal. So what would be the case? That would be XB, XA, cos 90. That is basically 0. One second, I think I have made it confusing for you. I'll just write it down, the expansion of all the forms, all the rotation matrices. So the first term would be XB dot XA. The second term would be XB dot YA. The third term would be XB dot ZA. And the second column would be YB dot XA, YB dot YA, YB dot ZA. Okay, so we'll continue. Yeah, the third column would be ZB dot ZA, ZB dot, sorry, it would be, yes, it would be ZB dot XA, ZB dot YA, ZB dot ZA. So this is how we would represent a general rotation matrices. So we would, let us fill the columns one by one. This be the first column. This would be the second column. This would be the third column. So what is the angle? We only have to look at the angles between the corresponding unit vectors. So XB and XA are basically coincident. They don't have any angle between them. So the first term would be, we will write the numerical values over here. So XB dot XA would end up in 1. And what would be the second element would be XB dot YA. XB dot YA. And XB over here, this is XB and this is YA. And as you can see, the angle between XB and YA is basically 90 degrees. So their dot product would be 0. And same goes for XB and ZA. It's still 90 degrees. So the angle between them is still 90 degrees. So the dot product would be 0. And what would be coming onto the second column? It is with respect to the rotated vector YB with respect to XA, YA, and ZA. So what is the angle between YB and XA? Because this is out of plane. If you are considering the plane of the board as the plane, the vectors XB and XB are out of plane. So the angle between XB and YA, sorry, the angle between YB and XA are still 90 degrees because YB is still in the plane and XA is out of plane. So the angle is still 90 degrees, so their dot product would be 0. Right. Now the second term would be YB dot YA. Now what would be the angle between YB and YA? If this is YB and YA, I'll use different ink. I have mentioned that the frame of reference B is rotated by an angle theta with respect to XA. So what is the dot product of the angle between YB and YA? It's just theta. So the projection of YB on YA, the projection of YB on YA is obviously YB cos theta, right? this term, the projection of YB on YA would be this length. This length. That would be YB cos A. That would be cos theta. Cos theta. Now the third term, this is your third term, YB dot ZA. That is the projection of YB on ZA. The projection of YB on ZA. What would that be? That would be projection of YB on ZA would be this length. That is nothing but sine theta. So we would get sine theta over here. Now coming on to the third unit vector, which is ZB, we would cyclically project ZB on XA, YA, and ZA. So what is the projection of ZB on XA? So ZB is on the plane and XA is out of plane. So the projection of ZB on XA is going to be 0. It's 0. And the second term would be the projection of ZB on YA. What is the projection of ZB on YA? So if you are projecting ZB on YA, so I'm extending YA on to the negative axis. And if I'm projecting ZB on YA, this would be the projection of ZB on YA. This portion would be the projection of ZB on YA. That would be, what would that be? This is 90 minus theta. This angle is, one second. I hope you agree that this angle is theta and this angle is 90 minus theta. So projection of ZB on YA would be minus sine theta because in the other because it is in the negative sign of Y axis. This is minus sine theta. And the final term would be the projection of ZB on ZA. And the angle between ZB and ZA is theta. So the projection would be cos theta. So Saurabh, I hope this is followable for the convention that we are following in robotics.
Yes, sir.
This is how
yes,
this is how we would derive the rotation matrices, and this is the general form actually. Right, the dot
yes,
product.
Sir. I'm fine with it, sir. Yes, sir.
Okay, so this rotation matrix is specific for the rotation about x-axis. So a rotation about x-axis would correspond to this matrix. So the first term would be 1, 0, 0. Like it will be 0, 0 for all the rows and columns from the first entry. And the remaining submatrix would be cos theta minus sine theta, cos theta. Yeah, and a similar procedure can be adopted for rotation about y-axis. Right? So if you are rotating strictly about y-axis, this would still follow a right-handed coordinate rule. So from the previous frame, XA is out of plane, YA and ZA are on the plane. But if we are reorienting this frame of reference, and if we are looking orthogonal to this direction, we would get, it would look something like this. So now YA is out of plane, XA and ZA is plane. Again, if we are using this same formulation, we would end up with a matrix something like this. This is the rotation matrix, rotation purely about y-axis. And the entries are cos theta, sine theta, cos theta, 0, sine theta. And on the second row, we have 0, 1, 0. And the third row, we have minus sine theta, 0, cos theta. Right? I'll take the second row, just the second row as an example. So the second row is basically the projection of YB on XA, YA, and ZA axis successively, right? So we'll just stop with the second column. So what is the projection of YB on XA? Because YB and XA, as you can see, XA and ZA are within the plane, and YB is basically out of plane. So the dot product between YB and XA is going to be 0 because the angle is 90 degrees. Now the second term would be YB dot YA, the projection of YB on YA, projection of YB on YA. As you can see, since both of them are coincident, the projection of YB on YA is 1. Their dot product is 1. And the projection of YB on ZA, again, just as in the case of the X coordinate, the Z A unit vector and YB unit vector are 90 degrees apart. Their angle is basically 90 degrees between them. And the projection of YB on ZA is going to be 0. So that corresponds to the second column. The projection of YB on XA, Y, and ZA. That is what it corresponds to the second column. So we would end up with a 0, 1, 0. And the same reasoning goes for the rotation purely about Z axis. So we'll get a different rotation matrix that will be cos theta minus sin theta 0, sin theta cos theta 0, 0, 0, 1. Right? Based on the similar reasoning, we can still derive or determine how to populate all the columns or all the elements of the rotation matrix. Okay, so now that we have defined how to define the position of a point and rotation of a frame, now how would we describe it together? How would we describe the position and orientation? So we if you can recall in the course, we have different cases actually, mapping involving translated frames alone. So in this case, we have two frames of reference. One is this one. It's called the A frame. That is the first frame we would mostly consider the first frame to be fixed on to the ground, and the second frame to be the moving frame. So here we would consider the frame A to be fixed on the ground and frame B to be moving. And as you might have observed, the orientation of both of the frames are identical. So XA is aligned with respect to XB, YA is aligned with respect to YB, and ZA is aligned with respect to ZB. And we have a point of interest that is called Q. So suppose that the position of the point Q is known with respect to frame B. So if we know the position of the point Q with respect to point B, if this is known, and we also know the position of frame B with respect to frame A, that is position of frame B with respect to A. If this term is also known, then what would be the position of Q with respect to frame A? That is the question. So we know the position of Q with respect to this frame, and we know the position of frame B with respect to frame A, and our objective is to find the position of the Q with respect to the global frame A. So due to the fact that both of the frames are aligned identical, there is no relative orientation between the frame. The final position is simply a vector addition of both of these vectors. So the final position that we are interested is just a vector addition of the known vectors. So position of B with respect to A plus position of Q with respect to B would give you the position of Q with respect to A. So that is simply this expression, right? That is only for this specific case when the mapping involves only the translated frames. But there are complicated cases where the mapping involves rotated frames. So consider this example where we have the fixed frame to be frame A, where XA and YA and ZA are aligned as such. And we have a rotating frame B, that is aligned as given in this figure, basically. So this is nothing but the frame B rotated 90 degrees with respect to XA axis. I hope you can see that. Consider both of the frames to be coincident initially. So what will happen if you rotate the frame B with respect to XA? So initially XB would be coincident with YA. If you rotate it by 90 degrees, YB would be vertically up. And initially, ZB would be coincident with ZA. And if you rotate ZB 90 degrees, it would end up here actually. That is where you would get as ZB. And since we are only treating rotations, we are not treating translations in this case, this distance is basically 0. The distance between frame B and frame A is basically 0. And just for illustrative purposes, I have given an offset. Just to make it more clearer, I have basically given an offset, but in reality, these frames are, the distance between these two frames are 0. All right, so again, another problem. So if the position of point Q, if the position of point Q with respect to B is known, this is nothing but, sorry, as per the notation, this is position of Q with respect to B is known, then what would be the position of Q with respect to A? What would be the position of Q with respect to A? That is simply given by the rotation matrix formula, right? If we know the position of P with respect to Q, and if we pre-multiply the position of Q with respect to the rotation matrix, that would describe the rotation between frame A and frame B, the rotation of frame B with respect to frame A. We would get the position of point Q with respect to position of frame A. So for an example, just for an example, I would give the coordinates of point Q as 0, 1, 0. Right? Position of point Q with respect to B as 0, 1, 0. So the point Q is located 1 unit along the y-axis of frame B. So yeah, if this is point Q, that is located 1 unit along YB, then what would be the position of, what would be the position of point Q with respect to frame A? Can anyone of you say that? Just by looking at the figure, if position of the position of point Q with respect to B is given as 0, 1, 0, then what is the position of Q with respect to A? What is this answer?
0, 0, 1.
Exactly, yes, 0, 0, 1. It's correct, because just by looking at it, the point Q is basically aligned with respect to Z axis of frame A. And due to the fact that both of them are coincident, due to the fact that the origin of A and B are coincident, the point Q will be exactly 1 unit in the direction of ZA. So even without applying the rotation matrix, you can basically see that, you can basically intuitively see the transformation. And just to prove it mathematically, I'll just construct the rotation matrix. We'll construct it column by column. So the first column is the projection of XB on XA, YA, and ZA successively. So XB is, as you can see, XB is aligned with XA. So the first entry would be 1. And the remaining entries would be 0, 0. And the second column would be the projection of YB on XA, YA, and ZB respectively. So that projection of YB on XA is 0. Projection of YB on YA is still 0 because they are orthogonal. Projection of YB on ZA is 1 because they are coincident. And the third column, projection of ZB on XA, YA, and ZA respectively. The position of ZB on YA would be -1 because they are opposite to each other. Sorry, the projection of ZB on XA would be 0 because XA is out of plane, ZB is on the plane. Projection of ZB on YA is -1. Yes, -1. And projection of ZB on ZA is 0. And we have also been given the position of point Q with respect to P as 0, 1, 0. And if we multiply this out together, what would we end up with? We would end up with 0, 0, 1. So this is the final answer that we are looking for. So I hope it is clear. We don't have any further issues in this aspect. This is purely related to frames with rotations, pure rotations involved. There is no offset. There are no offsets in this particular problem. Okay, so moving on to the final case, where the mapping involves both translated and rotated frames. The expression for, if you want to describe the position of Q with respect to frame A, this would be the correct expression. Because earlier, this offset was 0. This was basically 0. This vector was basically 0 because we considered both of the frame to be coincident. And now, due to the fact that there is basically an offset, what would be the expression? Like if position of B, position of Q with respect to B is known, and the orientation of the frame B with respect to A is also known. What is the position of the point Q with respect to point A? It would be simply from this expression. So first we would convert the position of Q with respect to B with respect to frame A using the rotation matrix. Then we would add this offset matrix. That's all. A simple vector addition would not be enough because position of Q with respect to A, just by going with vector additions, it'll be like P AQ would be P AB plus PBQ. So just by going with vector additions, we have PAQ would be PAB plus PBQ. But this is not the correct answer. We have to bring everything with respect to a single frame. So we have to bring everything with respect to a common frame A. So PAQ, or the position of Q with respect to A, is what we have to find out. Position of P with respect to, position of P with respect to A, we already know in terms of frame A. And position of Q with respect to B, position of Q with respect to B. In the question, we only know in terms of frame B. In order for us to convert it into frame A, we have to pre-multiply it with the rotation matrix. So this is how we proceed with problems that involves both translations and rotations. Yes, and rather than multiplying the transformations as components of position and orientation, we would make use of something called a transformation matrix that would take care of both rotations and translations as a single mapping. So we have a 4x4 matrix actually. This would take care of both positions and orientations. A homogeneous transformation matrix. This is basically of order 4x4. And the first 3x3 submatrix is just the rotation matrix. And the final rows is basically 0, 0, 1. This is the same for all the transformation matrix. The final row would be 0, 0, 0, 1. And the fourth column, the first 3 elements of the fourth column is the position vector. So I hope you can see how easy this is. So if we know the transformation between frames A and B, and if we know the transformation between frames B and C, and if we want to know the final transformation between frames C and A, if this is what we want to know, if both of these are known, this is only a matter of matrix multiplication. The transformation of C with respect to A would be transformation of B with respect to A times transformation of C with respect to B. So multiple such transformations can be the combination of rotations as well as orientations can be brought together in form of can be consolidated in form of a single matrix, such that the final transformation matrix is only a series of matrix multiplication. It's that straightforward. And if you want to find out the inverse of the transformation matrix, it is given as per this formula. The inverse of the transformation of B with respect to A would be the transformation matrix B with respect to A inverse, where the first 3 by 3 matrix block would be the transpose of the rotation matrix. This is nothing but the transpose of the rotation matrix. Anyway, like since this is also transformation matrix, the final entry would still be 0, 0, 0, 1. And the first 3 entries of the fourth column would be as such. It will be minus rotation matrix transpose multiplied with the position vector position of P with respect to A. And the derivation of this inverse is already being discussed in the lectures, how you derived this rotation matrix. It's nothing but if you solve this problem, if you know the rotation matrix A, RB, A, PB, 0, 0, 0, 1. So the transformation matrix times its inverse, let the components be x, y, 0, 0, 0, 2. This would be an identity matrix. This would be nothing but an identity matrix, because a matrix times its inverse would give you an identity matrix. So if we solve this problem, this matrix problem, and if we solve for x and y, where x corresponds to this term and y corresponds to this term, you would end up with this exact equation, right? It's straightforward. It has already been discussed in the lectures. Feel free to visit the lectures if you are not familiar with the concepts. And again, one final but very important aspects of compound rotations are to know whether transformation is applicable if you pre-multiply with the current transformation or if you post-multiply with the current transformation. But when to pre-multiply and when to post-multiply is basically a question. So I'll give you a brief example of what I'm talking about. So for example, if you have a frame of reference, a global frame of reference that would be named as XA, YA, and ZA. And we also have a coincident moving frame of reference. So at the initial position, let it be coincident. Let it be ZB, YB, and XB. So initially, the fixed and the moving frames are both coincident. So now the transformation matrix between the frame A and frame B would be identity matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. Because there is no relative rotation about both of the frame. Okay, suppose if we are rotating the frame B with respect to x-axis, so rotate B with respect to XA axis, right? So if we want to rotate the frame B with respect to XA axis, do we pre-multiply or post-multiply? So if we are rotating with respect to an axis of the fixed frame, we always pre-multiply, right? As per the first statement, if you see the first statement, if the mobile frame is to be rotated by an angle theta about the kth unit vector of the fixed frame, then pre-multiply with the rotation matrix. So if we are rotating with respect to XA, we pre-multiply the current transformation matrix with the new matrix, actually. Sorry. Yes. So rotate, the first problem would be Problem 1 would be rotate frame B with respect to XA by theta. So since frame B is rotated with respect to XA, that is part of the fixed axis, we pre-multiply the existing transformation with theta. So it would be cos theta minus sin theta 0, sin theta cos theta 0, 0, 0, 1. Okay, so now the XB frame would end up something like this. YB would rotate theta degrees. This would be the new YB dash. XB would still rotate by an amount theta. This would be, sorry, ZB dash. XB would still be in coincident with XA because we are rotating this with respect to XA axis. Okay, now if you are taking it further, now for problem 2, if we are rotate beta with respect to YB dash. Now, how would this be actually? How would this transformation matrix would be further extended? How can it be further extended? Can anyone chip in? Saurabh or Murali, can anyone chip in? Like if now for the second problem, if you are rotating with respect to YB dash axis. Yeah, I guess I've got a message. Post multiply with rotation matrix. Exactly, yeah. Murali got it right. So now make note that we are rotating with respect to YB dash. That is part of the moving frame. So as per the second statement, if we are rotating, if the mobile frame is to be rotated by an angle theta about its own axis, then post multiply with the rotation matrix. So if we are rotating with respect to the moving frame, then we'll have to post multiply. So due to the fact that this is rotation about y axis, the post multiplication would be with this matrix: cos beta 0, sin beta 0, 1, 0 minus sin beta 0, cos beta. This is how it would the entire transformation would look like. So depending on with respect to which frame you are rotating, you have to either pre-multiply or you have to either post-multiply. And the order of this multiplication is very important because we all know that matrix multiplication is not commutative. So the order is actually very important. So yes, I guess this is basically a review of the topics that we have covered for week 1. We'll now move on to some sample problems that would probably help you to solve the assignments. I suppose the deadline is still not finished. Maybe you could solve as we go through the tutorial. It'll probably help you. The contents are more or less the kind of questions that we are discussing here are more or less in line with the questions that you could expect in the tutorials, in the assignments actually. Yes. So for the first question, it says in effector, if the effect on the environment causes the motion of the effector itself, it is called as. So which of the following option is correct? So the keyword to note is effect on the environment causes the motion of the effector itself, right? So basically, we have covered two kinds of effectors, which are locomotive devices, and manipulations. And the rest of the options are basically not applicable. And which of the options out of these two is correct? Can anyone of you chip in? I guess. Okay, I got
Is it locomotion?
It's correct. Yes, it is locomotion. I think I've got a message from Murali from the previous question. Will the pre and post multiplication hold of transformation matrices as well? Yes, it will hold. So if the transformation matrix is with respect to the current frame, you have to post multiply. If it is with respect to the global frame or with respect to the fixed frame, you will have to pre-multiply. It will hold exactly with the same principles. I hope that is clear. Yes. Now, yeah. So we have got an answer. The correct answer is locomotion. Yeah, as per the answer key, the answer is indeed locomotion. Yeah, and for question 2, it's a fill in the blanks kind of a question. You could expect such questions for your assignments as well. So a dash robot manipulator has more than one loop. The end effector is connected with multiple serial chains. So what are the different kinds of manipulator that we have come across in the course? We have come across serial manipulators, and we have come across parallel manipulators. And then a combination of serial and parallel, which are called hybrid manipulators. But which of these options is the correct answer with respect to the question? I hope we can all agree that the correct answer would still be, it's still the parallel robots, right? I don't think we have any confusion in this regard. Yes, parallel, yes. I think Murali has answered it to be parallel, yes. If you have any concerns or if you have any conflicts with respect to the answers that I'm sharing, please do let me know. Okay. Yeah, moving on to the third question. In dash workspace, the entire set of points can be achieved, but in some of these points, not all possible orientations are achievable. So which would be the correct answer? We have basically come across two different kinds of workspace within this course. We have come across dexterous workspace. We have also come across reachable workspace. We haven't basically discussed anything about total workspace and dead workspace. We haven't covered, or it's not part of our course. So out of these two options, which of them is the correct answer? Again, I've got an answer. Reachable workspace as per Murali, dexterous workspace as per Saurav. We have got two conflicting answers. So again, the question, I hope the question is clear enough. The entire set of points can be achieved, but in some of the points, not all possible orientations are achievable. All possible orientations are not achievable. So if we have a point, we would want to achieve it in all possible orientations, whether it like this, the gripper has to achieve it like this, or like this, or like this, or like this. Infinite amount of configuration should be possible. Then only we can call it as dexterous workspace. Otherwise, if it can only achieve a composition with a limited amount of orientations, then it is called a reachable workspace. So the answer is indeed reachable. I hope that is clear in this case, because not all points can be reached with all possible orientations. So dexterous means we can achieve all the orientations in all points in all possible orientations. So I hope that is clear. Okay, be careful with these kinds of questions. It's easier to make mistakes. So the answer is still reachable workspace, not dexterous. Okay, so this is basically a numerical problem. Yeah, we have been given two rotation matrices, A with respect to B. We have been given two rotation matrices. Rotation of B with respect to A is what we have. We also have rotation of C with respect to B. And the question asks, find the rotation matrix C with respect to A. What is the rotation matrix of C with respect to A? So how would you tackle this problem? Again, I've got it. Okay, yeah. So again, I should warn you that the session will still is still going to run out within 2 minutes. So please try to rejoin within the same link once the connection is going to terminate. We'll resume the session again once it is automatically terminated. So before that happens, we'll try to make progress. So rotation matrix of B with respect to A is given. Rotation matrix of C with respect to B is given. What is the rotation matrix of C with respect to A? This is simply a multiplication of B with respect to A times C with respect to B. I hope we can all agree with that, right? Because we have a frame A, we have a frame B, we also have a frame C. So rotation of B with respect to C, we already know. Rotation of A with respect to B, we already know, but we don't know the rotation of C with respect to A. This orientation we don't know. So in order for us to find out that, we have to multiply the known rotation successively. That would be, again, the order is very important. As matrix multiplication is not commutative. So it would be 1, 0, 0, 0, 0, minus 1, 0, minus 1, 0. This times 0, 0, 1, 0, 1, 0, 1, 0, 0. And if you multiply this out, so if you multiply the non-rotation matrices, A with respect to B and B with respect to C, the final result would be somewhat like this. The first column would be 0, minus 1, 0. The second column would be 0, 0, minus 1. The third column would be 1, 0, 0. And the option corresponding to that is option A. That is the correct answer, right? So sometimes the question might be, the question may be different actually. So in this case, we have three rotation matrix. ARC, we have ARB, and we have BRC. So in this problem, we know the rotation matrix ARB and BRC were given, and we were asked to find out ARC. But in the case where we are given these two matrices, BRC and ARC are known, how would you find ARB? If this was the problem, how would you find out ARB? If ARC, the total transformation matrix is known, total rotation matrix was known, and BRC was also known, how would you find this rotation matrix? So does anyone have the correct answer for this problem? You can use your microphone.
Do we pre-multiply both sides with the inverse of
Okay.
BRC?
ARC pre-multiply with BRC inverse.
Inverses.
Okay, so I am going to pre-multiply with BRC. This would be equal to ARB. Sorry, pre-multiply, right? Sorry.
Yes.
1 second.
Yeah, ultimately we would get ARB on the right hand side because
yes. So let me write it. BRC inverse ARB BRC. You said you would pre-multiply this with inverse. This is what you said, right? And ultimately we would end up with?
Yes.
Okay. Are you sure this is correct? Is it pre-multiply or post-multiply? Because think for a moment actually. What happens if you post-multiply? We have I'll rewrite the problem again. ARC is ARB times BRC. So as opposed to your suggestion, if I post multiply BRC inverse And on the left hand side also, I post multiply with BRC inverse. What would happen? This is an identity matrix, right? A rotation matrix times its inverse is identity matrix, right? So this
Yes.
entire term would get cancelled. This term on its entirety would get cancelled. This is basically an identity matrix. So ARB times identity matrix is still ARB. And here you would have a different matrix. This would be ARC times BRC inverse. This would be equal to ARB, right? So as per your suggestion, it was BRC inverse ARC is ARB. I don't think that is right, because if you take a look at to the suggestion, if to take a look at what you have suggested, you would end up with this equation. No, that is not same as this equation, right? Because in the left, this was the original equation. If you we want to isolate the unknown, we want to isolate ARB. If we want to isolate ARB, we have to post multiply this with BRC inverse. Then only this term would get this term would become an identity matrix, right? If we post multiply, you would end up with this thing. This would not end up with ARB. This would not ideally end up with the expression that we are looking for.
I understand now. Thank you.
Yeah. So that we have to be careful with that. You may get a different problems for your assignments. It does not have to be this straightforward. In the assignments, it could be twisted. It could be combinations of the questions that you are getting. So you have to be very careful with respect to the order of which you will be multiplying with the matrices. Okay. Okay. So yes, the correct answer, as we have discussed, is indeed option A. Okay. So next question is, if you are given a rotation matrix, how would you find its inverse? How would you find its inverse, actually, if you are given a rotation matrix?
So would it just be the transpose of it?
Adjoint A by determinant of A. Yeah, exactly. So the actual formula, even though the actual formula is adjoint A by determinant of A, in case of a rotational matrix, since it is an orthogonal matrix, you only have to take its transpose, because R transpose is R inverse, because R is a orthogonal matrix. So if you want to find its inverse, you only have to take its transpose. So the transpose of the rotation matrix would be 1, 0, 0, 0, 0, minus 1, 0, 1, 0. And the option corresponding to this is, I guess, option A, right? Yes, option A. Yeah, that is indeed correct. I hope. Okay, I'm still getting some chats. Okay. Yes. I hope it's clear. Yeah, we have a true or false question. Okay, what does it say? If the mobile frame is if the mobile frame is to be rotated by an angle theta about the kth unit vector of the fixed frame, then post multiply with the rotation matrix. So is this true or is it false? So rotation about fixed frame, rotation about moving frame. And we have two different options, whether it is to pre-multiply or whether the correct answer is to post-multiply to get the subsequent transformation. So we have basically reviewed this thing in the review just before we started solving the questions. Murali says it's false. Saurav, do you have an answer for that? Is it false or is it true? Okay. Okay, so the correct answer is indeed false. So if the rotation is about fixed frame, we pre-multiply. Always keep this in mind. And if the subsequent rotation is specified with respect to the current frame or with respect to the moving frame, we always post multiply to get the subsequent transformation. Okay, that is indeed false. The correct answer is indeed false. Yes. Okay, moving on to the seventh question. I guess we have in total 9 questions. So this is the seventh question. So we have been given a transformation matrix, transformation of B with respect to A. We also have transformation of C with respect to A. We have to find the transformation of C with respect to B. This is, both of these are given. We are supposed to find, we are required to find this one. So as per the transformation, as per the forward multiplication rule, ATB would be ATC, sorry, ATC, we have to find out, yeah, we have to find, what was the, okay, 1 second. We are given transformation of, we have been given transformation of B with respect to A are given. Yes. We also have been given transformation of C with respect to A. So we have to find transformation of C with respect to B. So transformation of C with respect to A is transformation of B with respect to A times transformation of C with respect to B. Right? I hope we can all agree with this law of transformation. We have 3 frames, frame A, frame B, and frame C. And frame B is the intermediate frame. And we are asked to find out this matrix, transformation of B with respect to C. That is the unknown actually. We know both of these matrices. Now, how to find out transformation of B with respect to C? So, Saurav, can you answer that? Given ATC and ATB, how do you find BTC?
This time we pre-multiply with ATB inverse.
Okay, ATB inverse ATC would be equal to ATB inverse ATB, then BTC.
Yeah.
Yeah, so this would be ATB inverse ATC. This would be an identity matrix times BTC. This indeed would be BTC. That is indeed correct. Yes, that is incorrect. So we have to pre-multiply ATC. This is already known. ATC is already known. We have to pre-multiply this with ATB inverse. Okay, then how do you find out ATB inverse? How do we find out ATB inverse? So given ATB is given as 0, 1, 0, 0, minus 1, 0, 0, 0, 0, 0, 1, 0, 2, 4, 6, 1. And we have already discussed in the sessions, right? If we are given a transformation matrix of this form, R, this is a 3 by 3 matrix, then a position vector 3 cross 1. Then the final row would be 0, 0, 0, 1 cross 3, then a 1. If you are given a transformation matrix like this, how do you find out the inverse? This would be R transpose, whatever you have as R, its transpose minus R transpose P. Then the final row would be exactly the same 0, 0, 0, 1. Right. So given ATB, if we are given ATB, what would be ATB inverse? So ATB inverse would be the inverse, the first three terms would be the inverse of the R matrix. So I hope you can see where the R matrix is. So in this case, this would be the R matrix, right? So if you are taking the transpose, it would be 0, -1, 0, then 1, 0, 0, then 0, 0, 1. And as usual, the final row would be 0, 0, 0, 1. We still need to figure out the three terms of the fourth column. What would that be? That would be R transpose minus R transpose P as per this term, right? So again, applying this 0, 1, 0, -1, 0, 0, 0, 0, 1. This multiplied by 2, 4, 6. This is R transpose, this is P, and we also should have a minus. So if you take the matrix product as such, what would be the final answer? What would be the position coordinates? It would be 0. I guess it is. Is it correct though? I think I made a mistake, I suppose.
It should be positive R transpose P.
Is it? It's minus negative R transpose, right? 2, 4, 6.
Yes, sir, it is negative transpose, sir.
Oh, sorry, it's negative one layer, but it's not transpose. It is RP minus RP.
No, I am very much
No,
sure.
sir, it is transpose.
It is R transpose.
It is a transpose.
Because,
yes, sir.
Yeah, for the sake of clarity, it should be like, yeah. What I'm trying to say is that if we have an R matrix, if we have a P matrix, if we have 0, 0, 0, 1, and if we multiply it with an inverse X and Y, 0, 0, 0, 1, we should end up with an identity matrix I. This is 0, this is 0, this would be 1. So if you multiply this out, this would be Rx, Rx. The first term would be Rx. The second term would be Ry plus P. The third term would be, the final row would be 0, 0, 0, 1. This would be I 0, 0, 1, right? So if you equate these two matrices, Rx would be I, so X would be R inverse or R transpose, and Ry plus P would be 0. Therefore, Y would be minus R transpose P. So that is indeed correct, right? It's X is R transpose and Y should be R minus R transpose P. So again, this whatever I have written here, is indeed correct only. That's indeed correct. Okay, so R transpose we have already found out. R transpose we have already found out that is simply a transpose of this one, that is 0, -1, 0, 1, 0, 0, 0, 0, 1. And in order to find out these vectors, it would be minus R transpose P. That would be 0, 1, 0, -1, 0, 0, 0, 0, 1. And taking out the P is, it's 2, 4, 6. So the matrix multiplication would be 0 times 2 plus 4. This would be 4. This would be -2. And this would be 6, I suppose. 4. Oh, okay. We also have a minus sign, I guess, right? Yeah.
Yes, sir.
We also, I'm sorry. We also have a minus sign here. So it would be -4 to -6. And this is A transpose B inverse. And as according to the problem that we are trying to solve, we have to multiply this with what do we have to multiply this with?
ATC.
Yes, ATC. That would be 1003 0 0 -1 5 0 -1 0 0 0 0 0 1. So if you multiply this out, this would be the first element would be 0. The second element would be, I guess it still be 0. The third element would be -1, and the fourth element would be 5 minus 4. I suppose it's 1, I guess. Yes. It's I'll rewrite this again for clarity. It's -4 to -6. And the second row would be -1 0. This would be 0. And the final element of the second row would be 4. Sorry. It would be 3 -3 plus 2. That would be -1, I guess. And the third row would be it would be 0. The second column would be -1. This would be 0, and final row would still be 0. No, yes, it would be -6, I guess. Yeah. 0 times 3, 0 times 5, 1 times 0, -6 times 1 is 6. Then the final term would be 0, 0, 0, -1. Yes, so this is our answer actually. Yeah. First column corresponds to 0, 0, -1. I guess the answer would be option A, I guess, right? -1, 0, 0, 1. 0, -1, 0, 6, then 0, 0, 0, 1. Yes, so in that regard, the answer is option A. So I hope we can remember how we arrived at this problem. It involved it involved finding an inverse of a transformation matrix and multiplication of two such matrices. So it involved two different operations to arrive at what we are trying to find out. And be aware that the inverse of transformation matrix is as per this formula. It's not transpose of the transformation matrix. But in case of the rotation matrix, the inverse of rotation matrix, it's transpose. Whereas in case of the 4x4 transformation matrix, the inverse is given as per this formula. Okay, so the answer is indeed option 1. Yeah, and this is a fairly straightforward question. The rotation matrix corresponding to 30-degree rotation about the positive y-axis is it option 1? Is it option 2? Is it option 3? Is it option 4? So yeah, rotation matrix about the positive axis of y is of this form: cos theta 0 sine theta 0 1 0 minus sine theta 0 cos theta. You can, if you are in doubt, you yourself can derive, like I have shown this earlier, how to populate the columns of the rotation matrix one by one. You can try this on your own if you are confused whether it is option B or option C. To get the correct signs, you can try it on your own. And as per the standard definition or as per the standard form, the correct answer is indeed option B. Cos theta, sine theta, 0 cos theta, 0 sine theta, 0 1 0. This is minus sine theta, 0 cos theta. So the answer is indeed option B. I hope we don't have any further questions on that. If you have, please let me know. If you are not clear in this regard, please let me know. Yeah, and the final question, if the operation space variables are given and the geometrical variables are known, then finding the configuration space variables is known as, is it transformation, is it forward kinematics, is it control, is it translation, is it dynamics, or is it inverse kinematics? So there are two keywords actually. It's operation space, operational space, right? And the second keyword is finding the configuration space variables, configuration space variables. So like operational space and configuration space, like these are more commonly known in a different name actually. Like most often we would use terms such as task space and joint space variables. So operational space and configuration space, these are just a different name for either of those two terms. So can you relate which of them are which of them is which? We have joint space, we have task space. So could you match the following? Could you match the first row with respect to the second row? If this is the first row and if this is a second row, could you match between the two rows?
The configuration space is the joint space and the operational space is the task space.
Exactly, correct. Okay, so I hope we don't have any conflict on this thing. Yeah, so we are, okay, exactly correct. So operational space is where the robot would operate or how the operation of the robot would be defined. So that would be mostly in terms of Cartesian coordinates if it is a Cartesian robot. For example, XY, this would be task space or operational space. And on the other hand, we have joint space or configuration space. Configuration space would comprise of the variables which would fully define the configuration of a robot. Maybe theta 1, theta 2, example. Again, XY are not the only parameters. Like if you have a 6 degrees of freedom robot, you have XY, you can also have Z, you can also have the 3 orientation parameters, theta, phi, xi. So I'm only giving XY as an example for task space, that's all. So in the question, it says, yeah, operational space variables are known. The task space variables are known actually. This entire thing is known. If we know this, then what is the mapping between the task space to the joint space? This is what it is asking. Is it inverse kinematics or is it forward kinematics? Any answers?
Inverse kinematics.
Yeah. Okay. Saurav has said it is inverse. Well, I don't think we don't have to further elaborate on that. The answer is indeed inverse kinematics. Right? So the other way goes for the forward kinematics. Check the answers. Yes, it is indeed inverse kinematics. Okay, so that is all about this week's session, week 1, and all the topics covered in this week. We have also discussed some of the sample questions. You can expect questions of similar level for your assignments or quizzes, as you would call. So yeah, I'm really sorry for the mess up for regarding this week's schedule. Maybe we can talk with the NPTEL team to sort it out for the upcoming sessions. Maybe from week 2 onwards, we can have somewhat flawless experience. Okay, so if you have any further questions, please let me know. You can always use the discussion forums. I would be happily be responding to you in the discussion forums. So again, thanks for coming. Thanks for staying until the end of the 2 hours. Right. So if you don't have any questions, I suppose we can end this session here now.
Yes, sir.
Okay, all right. Yes. So again, thank you very much. I am ending the session now. Okay. See you next week. Bye.